So let us start our discussion today. We shall be talking about H1 in the external spiral galaxies. Well, we have already discussed in detail about H1 emission and absorption. So I will take on from there. I'll start by writing down the expression for the specific intensity. So this you should find from your notes on the radiative transfer of energy. And then when you go to the two-state systems, we talked specifically about H1 there. So this is the H1 specific intensity, which is defined at a particular direction in the sky. And here we have, by the vector theta, we mean the following. So we say that we see this part of the sky using a telescope. And this is the center of, so this I call the field of view. This is the center of the field of view. Imagine a Cartesian coordinate system here. So this direction I call theta x, this direction I call theta y, and any point in this can be written in terms of this vector theta. So that's what I mean by I theta. So this, when I say I theta, this is the specific intensity at that point in the field of view. It also depends on the frequency because it's a spectral line. And what is the specific intensity? So in the right hand side, I have 3 Planck constant, the rest frame frequency, which is 1420 megahertz, AUL, which you remember is the Einstein A coefficient by 16 pi. I have the column density at that particular direction. So this is the density integrated over the line of sight. The unit is like atoms per centimeter square. And then I have the line shape function, which may depend on the direction I'm looking at. It's also obviously depend on the frequency. Now, if I look at the line shape function, it can be written this way. This is a simple model for the line shape function. It will work for us. It's a Gaussian line shape function. If I integrate over the entire line shape function over nu, I will get just unity. It's normalized so that it happens. The spectral line is picked not at nu equals to nu 0, but the peak is shifted there, and where nu 0 is again the rest frequency of the line, 1420 megahertz. And I get this factor, the VL, which is the line of sight component of the velocity of the cloud divided by the speed of light. Sigma nu is the width of the line. Well, what is VL? The line of sight component of the velocity of the H1 cloud. It has 2 components. Now the H1 cloud from which the emission is coming, of which this is the specific intensity, is a part of a galaxy. So it's a part of a galactic disk, which I have drawn with this cartoon. And this galactic disk, all the galactic disks can have a certain velocity with respect to us. So the galaxy itself may be moving away or coming towards us. And that you can imagine as the velocity of the center of the galaxy if you wish. And that I have written as in terms of Vg. So this is the line of sight component of the galactic receding velocity. On top of that,
I didn't get that.
On top of that, sorry for that interruption. On top of that, I also have this disk being rotated. And because this disk is rotated, again, from the rotation, I will get a line of sight component of the rotational velocity. And now that will be different at different position of the disk, because if you imagine this is being rotated, this part is going away, so it will have a certain velocity of going away, but this part will be coming towards you. So it will have a certain velocity of which is towards you. This is the velocity which is going away. So the line of sight velocity is clearly different at different parts of the disk. On top of that, the disk not need to be in a face-on orientation, and by this time you know what is face-on, where you can see the entire disk of the galaxy like this. It can have any orientation, and the orientation it has with respect to face-on, we call it inclination angle. So if it has a certain inclination angle, then this line of sight component of the rotational velocity will be related to the tangential rotational velocity, which is the velocity that is being shown here essentially. What is the, if I draw, if there is a cloud here and it's going this way, At this particular point, it has a velocity pointing this direction. So that's the tangential rotation velocity. And if I take the modulus of that, then the line of sight component of the tangential rotation velocity is related to that. The line of sight component of the rotation velocity is related to the tangential rotation velocity this way. This you can figure out just doing a coordinate transformation. And the inclination angle appears here. For a typical galaxy, the inclination angle itself can be different at different radius. It is not necessary that at all the radius the disk has the same inclination, but for the time being we are assuming it has the same inclination. Also, the disk orientation I have shown that the inclination is keeping this axis constant, but this axis can be anywhere. So this ellipse now can be rotated like that or anything that you may like. So all these are possible. So these are the components of the specific intensity that we have talked about. So till now we have discussed what is the specific intensity, what are their different components, column density, then the line shape function. The line shape function has this VL, which is the line of sight component of the velocity, which has the galactic velocity plus the rotational velocity. Now, what are the observables? One of the observable is the specific intensity itself. So it will be a function of 2 theta and 1 frequency. So this will be given as a function of 3 variables, which means I can think of a cube in which this function is given. Cube means cube has 3 axes, and along these 3 different axes I can have theta x, theta y, and nu. Or what you can do is you can think of different parts of the cube. Like for example, if I have a cube, I have this different, just a second. So let me draw for you what I mean. So I have this one square in the cube, and then I have another square, then I have another square. So let me give these a different color so that it is easier for you to understand. I have another square, and then if I choose a different color, I have another square, like that. So the cube now I have broken up into different squares, and for different squares you may think that the frequency is different, and these are like the x and y axis that I was talking about. So this is one way of looking at the data. The other way of looking at the data is integrating this over different things. So let us look at those observables. So here I point out those observables. So I take this and I integrate over all frequencies. So what is that you are expected to get? Well, the frequency dependence in this only comes in the line shape function, and as I have said, it is defined so that if I integrate it over all frequencies, you just get 1. So then what I will be left with is the column density multiplied by this number. So this is a number which you can calculate given that you know H, nu naught, and AUL, and that those things are quite well known. So you can calculate these numbers, which means that if I integrate this over the frequencies, what I get essentially is column density scaled by a known number. So I can get the column density out of it. So this is called the moment zero map of the galaxy. And we'll look at the moment zero map one of the real galaxy today. So this gives you the column density. Then what I can do is I can multiply it by nu and then integrate over all nu, sorry. So I can multiply the specific intensity by nu, the frequency at that particular that nu, and then I integrate over all nu. So what will happen then? Well, if you look at again, the nu dependence comes from here. So this is a Gaussian. If I integrate a Gaussian, multiply it by nu, what I am supposed to get back is this, which has the information about the line of sight velocity. It will be scaled by the moment zero map. So usually when you define this as the moment one map, you divide or scale it by the moment zero map, or normalize it by the moment zero map. So this now has the information about the line of sight velocity. So you see the physical parameters of the galaxy, the column density, which is related to the density of H1, the velocity, which is related to the dynamics of the H1, these you can get from the moment 0 and the moment 1. But remember that these are function of theta, which means you have to have a telescope which is good enough such that you can resolve the galaxy. You can look at different parts of the galaxy separately. If you don't have such a telescope, which is the case of the single dish observations in radio astronomy, then obviously you cannot look at different theta separately. You essentially see an integrated effect. So that's what a single dish telescope will see, where you will essentially integrate the specific intensity over all theta directions. And if you do that, what will you get again? If you do that, I have now integrated over this, so what I will be left with is the line shape function. But you remember that the line shape function is also a function of theta, so I will get not a Gaussian, but a more complicated line shape function, which will tell us more about the galaxy. Even interestingly, it tells us about something about the rotational velocity.